Hello, and welcome back to our topic, Review on Basic Stoichiometry. Please bring out your calculators so that we can calculate the problems together. In this review, we will look into law of conservation of mass, chemical equations, and stoichiometric calculations. Law of conservation of mass states that mass is neither created nor destroyed in chemical reactions, according to the observations done by Anton Lavoisier. So we will look into how our law of conservation of mass is applicable in our chemical reactions. The law of conservation of mass in chemical reactions would mean that the amount of elemental species present in our reactant side will be the same amount in our product side. We have here the combustion of methane, so let's use this as our example. Let's list out the elements that is present on both sides, and let's count and compare if the amounts are the same. So we have one carbon on this side and also one carbon on the other side. For hydrogens, we have 4. And for the product, we also have 4. And for our oxygen, there are 4 oxygens on this side. And there are also 4 oxygens on our product side. And this proves the law of conservation of mass. This then makes the law of conservation of mass as the backbone for balancing of equations. Let's use these 4 equations as an example. So Fe plus Cl2 will yield FeCl3. To balance this out, we will need 3 on this one, 2, and to balance our iron, we will need to put 2 here. On our next number, we have iron plus oxygen to yield your Fe2O3. So clearly, you can see that there are differences on your subscripts. So first, let's balance our oxygen. And then, of course, we will need 4 on our iron to make this a balanced equation. On the third one, let's look into it. And then we have 6 hydrogens and we need 6 bromine and then 2 iron. Is this balanced? Yes, this is already balanced. And for the last one, let's look into it. Let's balance our carbons first and let's see if we will be able to balance it out as easy. So C is 4. And then our hydrogen on the product side would be 8. So 6 plus 2 is already 8. And our oxygen is 2 times 2, it's 4. So we have here 3 plus 1, it's 4. So therefore, the coefficients for this equation is 1, 1, and 2. Now that we know how to balance our equations, let's move to stoichiometric calculations. We will review your ICE table, your limiting reactant, and excess reactant. Let's proceed. So what is ICE table? ICE table is your initial, change, and equilibrium table. So this will help us in calculating for the amounts of chemical species at the end of every reaction. Let's use this as an example. How many moles of carbon dioxide will be produced when 1 mole of carbon reacts with 1 mole of oxygen? Let's first write our chemical equation. It's C plus oxygen yielding CO2. Is the equation balanced? Yes, it is already balanced. So our given states that we have 1 mole of carbon and 1 mole of oxygen. Assuming complete reaction, all of your carbons and all of your oxygen will be consumed. And of course, Since CO2 is our product, we need to add 1 mole on this side. For the equilibrium concentrations, it's just 0, 0, and 1 mole. Therefore, 1 mole of carbon dioxide will be produced if 1 mole of carbon reacts with 1 mole of oxygen. Let's do another example. A sample consisting of 0.5 moles of X is placed into a system with a volume of 0.750 liters. At equilibrium, the amount of sample X is known to be 0.350 moles. What are the equilibrium amounts of the compounds if the reaction follows this reaction? Of course, let's first write our reaction, and then let's write our given. Our given states that we have 0.5 moles of X, and at equilibrium it's 350 moles. So we need to calculate for a change. So it's 0.5 minus 0.350. What is our answer? It's 0.15. So we will place 0.15 moles here. And on the product side, we will place the coefficient 3 divided by the coefficient of X, which is 2 times 0.15. And we will do the same with our Z, wherein we will place the coefficient 4 at the top and then 2 at the bottom multiplied with 0.15. Why do we need to do this? This multiplier over here signifies the conversion of X to your Y and your X to your Z. So what are our final answers? Now let's look into the limiting and excess reactant. We know that the limiting reactant limits the reaction, and the excess reactant is the reactant present in excess. But how will we know this if we are dealing a problem? Let's use this as an example. What mass of carbon dioxide forms in the reaction of 0.25 grams of glucose with 40 grams of oxygen? Let's start our calculations. The given is 25 grams of glucose and 40 grams of oxygen. First, we have to convert this into moles. So we have to divide this by your molecular weight. And the answer is 5 over 36 moles. And we have your 5 over 4 moles. How do we know if a reactant or a species is the limiting reactant? First, we have to divide the number of moles by its coefficient. So 5 over 36 divided by 1 is just 5 over 36. And 5 over 4 divided by 6 is 5 over 24. Then we compare which value is smaller. Is it 5 over 36 or 5 over 24? Since 5 over 36 is smaller, this would suggest that your glucose is our limiting reactant and our oxygen is the excess reactant. Now we can proceed and assume that all of our glucose will be consumed. So we have to subtract this by 5 over 36. And on this side, we have to subtract 6 over 1 because 6 is the coefficient of oxygen divided by 1, the coefficient of glucose, times your 5 over 36. And that is the same on the product side, but we will use addition. So what are our equilibrium concentration? Here it's 0. For oxygen, it will be 5 over 12 moles. For carbon dioxide, we will have 5 over 6 moles. And for oxygen, it's also 5 over 6 moles. Now let's look into this reaction and solve this problem. It says calculate the mass of magnesium oxide possible if 2.4 grams of magnesium reacts with 10 grams of oxygen. Let's start calculating. The first step is to write our given. We were given 2.4 grams of magnesium and of course 10 grams of oxygen. Next that we have is, let's look if our general equation is already balanced. So we have here O2, so we need to add a coefficient of 2 on this side. And to balance your magnesium, we have to add a coefficient of 2 for our magnesium. Now it's balanced. Next is we need to convert your grams to mole. So 2.4 divided by 24.3 and 10 divided by 32. So the answers, if we converted, it's 8 over 81 moles, and the other one is 5 over 16 moles. Now, we have to calculate which is the limiting reactant and which is your excess reactant. So 8 over 81 divided by 2, you will have your 4 over 81. And 5 over 16 divided by 1, it's still 5 over 16. By comparing these two, we know that 4 over 81 is less, so this is your limiting reactant, and oxygen is the excess reactant, meaning all of our calculations will depend on our magnesium. So for change, we will consume all of our magnesium. Here, we will write the conversion, which is 1/2 coefficient of oxygen over magnesium times 8 over 81. And on this side, we have to add, and then what are our equilibrium concentrations? This is 0. For oxygen, it would be 0.2631 moles. And for magnesium oxide, it will be 8 over 81 moles. Did you get that? Okay, good. Now that we've refreshed our memories regarding basic stoichiometry, we can now go back and calculate our Van 't Hoff factors. See you in the next video.